Hi, I'm Gaëlle Candel. I'm PhD candidate at École Normale Supérieure de Paris, and I will present my work on tagged documents co-clustering. The presentation will be decomposed into 4 parts. First, I will start with a little bit of context to understand the problem and the goals. Next, I will detail how data are preprocessed, which is important to deal with sparsity. Then, I will present the clustering algorithm and explain the different choices. I will follow with the results and finish with the conclusion. So, let's start with the context. We want to cluster a corpus of tagged documents. More formally, it could be represented as a bipartite graph with documents in one side connected to tags on the other side. In this context, there are different points to highlight. We have tags, not words, so their number per document is more limited. Additionally, there is no tag order. We only have a bag of words. Next, we don't have frequency, just present or absent. And last, tags, like words, follow power laws. The preprocessing deals with these different points, allowing to cluster data more accurately. We are interested by clustering for different reasons. In our case, we want to identify groups of similar documents and be able to characterize them using vocabulary groups. Clustering is helpful in other contexts. For instance, for query refinement, a user query is often short and with approximate vocabulary, limiting the match with the real document. By clustering words by related concept, it improves the match with the document description. For cluster retrieval, if items are grouped by clusters, it reduces the search complexity. Instead of comparing a query to a large index, the query is compared to a cluster summary index, and then compared to the index of the most relevant cluster. Last but not least, it could be used in collaborative filtering recommender systems. Users are clustered into communities, while items by categories. With clustering, the goal of the recommender system is to suggest items to a user based on the categories relevant to its community. This drastically reduces the computational complexity of the system, as the recommender system deals with much smaller matrices. To summarize, clustering could help to characterize groups, improve search accuracy, and enhance scalability. This type of dataset is often represented using the vector space model, where the bipartite graph is represented using a binary matrix. The main drawback of this representation is the dimension relatedness. Consider the set of items lion, tiger, and frog. We have the following representation vector 1, 0, 0, 0, 1, 0, and 0, 0, 1. Therefore, the distance is 2 for any couple of different items. However, we all know that lion is closer from a tiger than from a frog. Some methods already deal with this problem. One is to use an external database like Wikipedia or WordNet to enrich the initial document vectors. However, we have the following disadvantages. It increases the matrix size, leading to a higher cost. As you need a database, you are limited by what exists, which is not transferable to other problems. Finally, there is an asymmetry between the way you process each side of your graph. Another possibility is to learn these relationships. This is only possible with a large dataset, and you have to carefully deal with sparsity and power law. The approach we propose enriches the binary matrix using the document and tag similarity matrices. Our approach has the different characteristics. It limits the contribution of highly frequent items to the benefit of under-frequent ones. It is symmetric, using the same approach for documents and tags. There is no need of an external database, and therefore preserves the matrix size. And last, it is parameter-free. From the binary matrix, we extract two similarity matrices, one for the documents, one for the tags. A similarity matrix corresponds to the first-order normalized co-occurrence of two terms. We transform this matrix into a transition matrix to represent the probability to observe one term knowing a former one. We need to perform a double normalization for several reasons. First, because it keeps symmetry, but more importantly, this is the core mechanism to reduce the influence of highly frequent items. So the two transition matrices are obtained by bistochastization. Finally, we obtain our final smooth matrix by multiplying the two transition matrices with it. A smoothed term could be understood as the way to have a particular tag in a specific document, knowing all possible transitions from all possible pairs of tagged documents. This process smooths the matrix and drastically reduces sparsity. Because of the bistochastization, the global mass of the matrix is preserved. However, this process must not be applied twice. Otherwise, we would have an over-smoothing that would prevent from extracting relevant information. Here we present the visual result over a synthetic dataset. On the left, you have different tiles filled with 0 and 1 with diverse proportion. On the right, you have the corresponding result. The boundary between the tiles are much more visible on this representation, even for the tiles that were not filled at start. We will use this smoothed form for clustering. There are different questions to ask before selecting or designing a clustering algorithm. The main questions are: do we know the number of clusters to find? And the second one is: how do we evaluate our clustering? Concerning the number of clusters, we are in the case where we don't know. In that case, hierarchical clustering is the best option, as the number of clusters could be defined a posteriori by pruning the partitioning tree. Within this category, there are two possibilities: divisive approaches, which start with a single cluster which is recursively split, and agglomerative, starting with one item per cluster and merging them together. Due to the complexity, agglomerative algorithms are more popular, therefore we follow this way. Just a few words about two-way clustering. With all dataset, tags are documents features, while documents are tags features. We can cluster tags and documents using separate processes with one-way algorithms, or exploit synergies with two-way algorithms, which cluster both at the same time. The second approach, when possible, often leads to better results, even if the goal is to partition only a single type of items. Among the two-way clustering, there is the choice to build big clusters, where a cluster has heterogeneous type of item, assuming a one-to-one correspondence between the tags and the document groups. In contrast, co-clustering does not make this assumption, leading to more expressivity and flexibility. We've set the class of clustering algorithm we want to use. Now we will discuss about which measure it must optimize. There are two levels to consider. The local cluster level, assessing the coherency within a cluster, and the global level, assessing the quality of the overall partitioning. Concerning the global level, we define a good partitioning as a partitioning with clusters of equivalent size. A clustering identifying one large cluster and many singleton clusters is called filtering or anomaly detection. We reject this type of outcome as no true groups have been identified. We propose to measure this goodness using entropy measure. To each cluster, we can assign a probability based on the number of items it contains. We get the partitioning entropy this way. We increment this measure by setting the critical size under which an item cannot contribute. Otherwise, the best state in the agglomerative algorithm will be the initial state where no item have been clustered yet. Last, to get a measure agnostic of the number of clusters we already have, we normalize the entropy by the number of clusters it exists, which leads to a value between 0 and 1, where 0 corresponds to a very poor partitioning. Therefore, for each possible pair of clusters to merge, we evaluate the variation of entropy it will lead to. This defines the path for improving the global partitioning cost. Now, we will detail the local quality measures. For simplicity, we will use X to represent samples and Y the features. A cluster of samples is represented by a vector of probability using the smooth matrix. The size of these vectors depends on the number of feature clusters. The sum is made over all samples together before normalizing, meaning that samples with very few features contribute less than items with a large mass. This allows to represent a sample cluster as a mixture of feature clusters. We measure the similarity of two clusters by looking at their divergence. We use the Jeffrey-Kullback-Leibler divergence, which corresponds to the symmetrized version, as the cost of merging cluster A to B must be identical to merging B to A. In total, we measure the cost of merging cluster A to B as the product between the global impact over the partitioning delta and the local impact considering the content. Starting with each item in the cluster, the algorithm works by evaluating which pair among documents and tag pairs has the lowest cost. This pair of clusters are merged together, and the process is repeated until there is a single cluster left for documents and tags. Our target dataset was a DBLP dataset. This is a citation graph with about 5 million documents. Each document is associated with metadata like title, authors, abstract, and keywords. The keywords associated with an article will be used to build the binary matrix. Because of the complexity of the algorithm, we cannot process the entire dataset. We limit ourselves to 10,000 documents on our regular laptop. We select documents the following way. We define a keyword of interest, like graph, cryptography, or biometry. We gather all documents associated with this keyword. Then, we sample at random the documents to match our computational resources. The process allows to obtain a subset with already related AI items, which facilitates the discovery of relevant clusters. We'll present two examples, one for biometry, the other for payment. The first figure shows the resulting tree with a dozen of clusters left unmerged with their relationships displayed. For each cluster, we kept the three most frequent words to understand the topic. On the top left, we can identify clusters related to image processing with gait analysis and face recognition methods. Below, other biometric authentication methods related to fingerprint and voice biometry are visible. We can see a cluster with biometrics, computer science, and speech recognition where keywords do not go together, especially speech recognition that will go with voice biometry. These keywords are highly frequent within our document subset, leading to an artifact, as in any case they are not classifiable due to the lack of negative information. On the right, we have a group of clusters indirectly related to biometry, like cryptography, internet, and human interaction clusters. The second example concerns payment. Here, we can also identify three main domains. On the left, everything is related to modeling and economy. On the right, the core payment technologies, and on the bottom, related technology which are not exclusive to payment. In this example, we can also identify a cluster artifact with payment, cash, and crowdsourcing, where the two first are the most frequent tags. When looking deeper, the other words are related to crowdsourcing. Except these two words, the cluster is coherent. As a conclusion, we propose a preprocessing method reducing sparsity and power law effects, at the same time using transition matrix derived from similarity matrices. We propose a hierarchical co-clustering algorithm taking into account cluster size and cluster content, allowing to obtain cluster of equivalent size and coherent items. These two methods combined have been applied over subsets of the DBLP dataset. In the proposed examples, groups organized around a topic and are of balanced size. Comparison with one-way clustering and other algorithms are left to the paper. As a future directions, we may explore ways to reduce the algorithm complexity. Another direction is to exploit the tree structure to adapt to a query depending on its precision, for instance. Thank you for your attention, and if you have any questions, don't hesitate to contact me.